Hi and welcome. This time around we've got the first part of a continuing project that has been rather, long in coming. It's the project that I showed the first part of, which was the needle dispenser here. And that first part of the project, all its only point of that whole process was to be able to stack a bunch of these needles up in a device and have them individually dispensed so they could be picked up by a robotic arm. I'm not sure about the robotic arm solution as the ultimate solution yet, but now that I've got them dispensed, I need to get them into the device that's going to laser weld this little tip on the end here. You can see where it's welded right there. Actually, I don't know if this one's been welded yet. I don't think it has. Yes, it has. But some of them, they're just pressed on initially because it's a hollow tube. And then a laser weld goes around and very carefully welds this. So here's my deal. The second part of this project is the laser welding fixture that will somehow take these needles one at a time, weld them, eject them, and load the next needle, all in an automated fashion. I'm not sure the robot arm will have a proper place to play here. We will find that out. But one thing I know with my current design idea, which may morph because this is somewhat complicated, is that may not use the robot in the final design, but we'll find out as I move forward. So initially, we have here a spindle, and this spindle is part of the laser welding rotary fixture. Normally it holds a 3-jaw chuck that screws on this brown and sharp threaded section here on the end. This way there'd be a 3-jaw chuck. I'm gonna make a fixture that screws on here myself that will hold these needles one by one. But however, the way the needles are gonna be ejected, rather than put them into the fixture and then take them back out of the fixture, that's kind of challenging. I'm gonna just push the needles one by one through this fixture and have them come out the back end. Except I don't want them to accumulate in here. If they were centered, you'd accumulate a whole bunch of needles inside the spindle, which would be kind of inconvenient. So I'm going to create a centering device, which is going to use this Delrin here that fits pretty closely down the center of this. And we're going to drill a hole right down the center of this guy. And I need to make this removable, easily removable. So I've got an interesting solution for that that I want to play around with here. And that's the part we're going to make today. We're going to cut off a piece of this Delrin. We're going to drill all the way through. I bought this 3mm drill bit for deep drilling. And we're going to try and make it so the needle will go right down the center of this, and then I can have a box in the back that will collect the needles. That's going to be my first step. And there are a whole bunch more steps to this, but this is where I'm going to start. And rather than, like a set screw or something to hold the Delrin in here, I've got an interesting design idea that I want to pursue. And so I'm going to do that instead, just because I find it interesting, and hopefully you will too. First steps, I turned the other side and cleaned it up. This is the back side with some extra length on it. And I want to turn it down so it'll fit in a ER40 collet in the back here. So I got to turn it down to 1 inch. And the point of that is so that I can index 4 slots on the back, or 6. I have one of these in 6-sided as well. Haven't decided whether I want to do 4 or 6. I think I'm going to go with 4 slots, but we'll see, because the curvature might make them too stiff. And basically what I'm going to do is, on the other side of this, there are going to be some leaves. I'm going to trepan a slot out of the middle of this and have a wedge that's going to screw in that'll pop these leaves out and press against the side of the spindle to keep it in place when you want it in place, and loosen it to pull it out when you want to pull it out. I thought it'd be an interesting idea to try. I think I'm going to go for 6, not 4. So I was just thinking about the curvature of this, that if you have a 90-degree section of this, the curvature is going to make that naturally strong, and when you try and deform it by pushing it out, it might want to break because it's, it's naturally stronger. So we're going to cut 6 slots instead of 4. So we're leaving about 50 thousandths. If you ever worked with Delrin before, you know how awesome it is to work with. If you haven't, I highly recommend you try it. It's like brass on steroids to work with. All of these ER2 and even the 5C collet to square or hex holders that I had in the past, they've all been ground. They were moderately expensive, but not terrible. This set was really inexpensive, and they literally just use hex stock. Look at that. They didn't even bother grinding it. So I have no faith that that's particularly well centered on there. Fortunately, all I'm using this for is a rough indication of where some slots should go, so I'm not overly worried about it. But boy, if I was, these things are crap. Could possibly fix them on the surface grinder, but you need to make sure you reference that center diameter and make sure everything's equidistant from the center diameter. So these are really crap. Here's the square version. Just used some inexpensive square stock. They did not make much attempt to, actually this one was milled square. So they made a little attempt to make it right, but really these need to be ground, so I should probably do that. Or just spend a little more money and buy a better set. That's probably a lot of advice I'd get out there. Just want to cut 6 slots in here. Their locations are only approximate. That's not anything particular. This is for the leaves that'll expand out to press against the spindle, the sides of the spindle. To locate this part in each of the 6 directions on that part the part of this Delrin rod here that I reduced down to 1 inch, I've got this hex block on the back of it. Very rough hex block, so not particularly accurate. I have sort of a 1.5, I don't know, this is like a machinist made 1, 2, 3 block, beautiful thing here as a spacer. And then an adjustable parallel. Tighten this, pulls up the ramp. So the adjustable parallel and a stop over here, where all I need to do is slide this guy back until it's touching the stop, hold this flat on the adjustable parallel and tighten down here, and I can just repeat. So next we need to get a appropriate bit to cut the Delrin. We're going to do 1/4 inch wide slots because that's the bit size I've got. I've got specific plastic cutting bits, so we're going to use those. The bit I'm going to use is this 2 flute. I believe it pulls the chips up out of the hole, which will also tend to want to pull the part up, so I got to be careful. But it's designed specifically for plastic, so we'll see what kind of edge we get. It is solid carbide, beautifully polished flutes in there, and very, very sharp. The depth I'm going to go in the x-axis is based on how deep I can cut with the trepanning cutter here that I'm going to use, because we're going to hollow out the center of this to leave those leaves floating free. And so it looks like it's about 1 inch, but I'm going to measure that, and that's how far we'll go in. I very roughly centered this within 5/10 thousandths kind of thing. I used just the edge of this cutter, rotated side to side. If I wasn't exactly right, it wouldn't be perfect. When I measured, I think I'm off about 5 thousandths, but we're going to go in 950. None of this is critical. Next up, we just rotate 1 section right there, go against the stop, and away we go. And that quite literally is it. Now we're going to trepan out the guts of this, leaving just these fingers sticking out. Oh, you know what? Before I take this out, why don't we chamfer these just to make them look prettier? For the chamfering, I'm just going to use my chamfering bit here. Could use a much sharper bit, but this is a countersinking bit actually. Just want to take that edge off. Setting the height on my trepanning cutter, loaded right here. This trepanning cutter is good for 35 to 50 something millimeters, which should be good. I may have a problem on the inside. I want to do 3/4 of an inch. That's 20 millimeters. No, this is the wrong trepanning cutter. I got to get a different one. All right, so I don't know if I can get to the inside diameter I'm looking for on this. I want to get the inside of this 3/4 of an inch. This may be a failed experiment, but what the heck, right? I didn't look at my trepanning cutters because I can't go down a whole lot smaller diameter technically than this. Well, let's just try it and find out. That's about as deep as I can go. That's not going to be enough, I don't think, because now I'm running into the outside edge. Maybe when I cut this next part. Oh, that's really sad. Yeah, I don't think that's going to work. Oh, bummer. I don't know if you can see here, but you can see where it cut in, and now this is free. Since I had to go to the smaller trepanning cutter, it doesn't go as deep, which is unfortunate. Yeah, we need a lot more material to come off actually, and I think this one's got the wrong angle to do it. Well, let's try it and see what happens. Maybe I can use the other one to clean up, I'm not sure. All right, that should be my final diameter, 3/4 of an inch. Well, it looks like that's as deep as I can go with the smaller cutter. When I measured this out, it was for the larger diameter trepanning cutter. And when I looked at that, I thought, oh, that's bright because it's 35 to 50 something millimeters, and the outside of this part is over 35, but I was going for a smaller internal diameter. Don't, my bad. So these fingers do flex. I can see that. I only need them to flex a few thousandths, like 5 thousandths. So this plan still might work. So we're going to try it and just go for it, right? All right, next up, I need to put some threads on this internal shaft here. I hope you can see it because I know it's black on black. But we need to thread this internal piece here so that we can screw a part in that will press these fins apart and hold on the spindle shaft, and that will hold this in place. We're also going to drill a hole down the center of this all the way through that will allow the needles to come down through the center to be collected on the output side. Now, there doesn't need to be a lot of force pushing on these fins. They only need to hold the spindle fairly lightly because there's not a lot of force trying to push those needles, you know, through here. It's just friction. That's all we're dealing with. So we don't need to make this really tight into the spindle shaft, although I think it'll get reasonably so. Okay, so to do those threads, I ran across some interesting observations that I want to share with you. If you're familiar with this, you can just skip ahead. But here is a standard right-handed external threading tool. Now you will notice that the threading tool here is just to cut threads on the outside of this. If I wanted to have a standard internal thread cutting tool, that would be on a boring bar. And this would be cutting threads on the inside of these leaves here, okay? Going all the way around on the inside. And this would be a right-handed internal insert. Now, here's where the interesting observation comes in. They actually sell inserts for external right and left hand and internal right and left hand. In reality, there are only two types of inserts. There's the left hand and the right-handed insert, if you want to look at it that way, because the external right-handed thread and the internal right-handed thread are actually left and right hand opposites of each other. If I were to use this on the outside, this would cut a left-handed thread on the outside of this part. On the inside, this guy would cut a left-handed thread, while this guy cuts a right-handed thread on the inside. So in reality, there are only two types of threads. There's one where the point comes out this side and one where the point comes out the other side, which we call right-handed. So right-handed would be the point out this side, left-handed would be the point out this side. When you go inside, things are reversed, and so that's where the confusion comes in. And I guess they sell these inserts to take away the guesswork from you, but in reality, they're selling you 4 different types of inserts when in reality you only need 2. So that's my take on that. Hopefully that was useful and not too confusing. So I need to put threads on the inside of the shaft here. So that would be a right-handed external insert like this. However, I obviously can't do that because the fins are in the way. So instead, I need to be on the inside with a boring bar, not this one because it's too big. So I need the threads coming, the point coming out the other side to cut those threads, which actually makes it an internal left-handed thread cutting tool, but it's actually a right-handed threaded insert as reference to the external threads. So here's another interesting observation. So what I can do is, here is a standard right-handed tool for internal threads to cut along the outside of this area here. I could, if this fit, use it to cut these threads as well by turning it upside down and running the lathe in reverse. Then I would go from inside to out using the Pyzinski method. So I would cut the thread from the inside out with the thread in reverse, and we'd be good to go. So you can actually get away with cutting most threads with just one type of insert, which is kind of an interesting observation, right? Anyways, what we're going to do, I actually bought a left-handed insert so I can cut from inside out, but because there's not a lot of room for relief in here, I might actually use a right-handed insert to cut this from inside out, running it upside down with the lathe in reverse, because that will make it easier to come back to the same point every time and not worry about crashing the threading tool into this plastic end here. I was hoping to cut this deeper, but I don't have a trepanning tool that'll cut deeper, and I didn't want to try and grind one because they start getting really weak and start wobbly. And although I get away with it most likely because it is plastic, it just didn't seem like it was worthwhile for this particular project. If I can try and make things a little more clear, this is a Micro 100 boring bar, solid carbide, for cutting right-handed threads on the inside of a bore along this outside edge here, right? But if I want to cut along here, I would need the left-handed version of this tool, which I do have if I want to cut from from outside to in. But what I'm going to do is I'm going to run this guy upside down, run the lathe in reverse, and go from inside to out. So I could use this one tool to do right-handed threads here or right-handed threads here, all with the same tool. I could also do left-handed threads on the outside with this guy if I wanted, or right-handed threads right here on the outside as well, going from inside to out. So one tool can actually do it all if you want to get creative. You don't need to buy tons of different turning inserts, but it can make it easier for you. So that's one reason why they sell them, for convenience. So I set my height with the insert upside down, or the cutter upside down. I guess this is a boring bar. So I've got the boring bar upside down, and I set my height right there so that it just barely touches, and we should be good to go. I hope you're gonna be able to see this, but first thing I want to do is put a lead-in chamfer on this. All right, so you can see I've got my boring bar over here, and I'm going to start from the inside. This is my 0 position on the inside. We're going to start the lathe in reverse. So you see it's coming up on the cutter, so it should cut right. First, I've got to put a relief area here. So the total depth I'm going to go is 43 thousandths. So we're going to go in 50. There's 50 thousandths. We're going to come out just a little bit to give me some clearance space there. Then I think I'm going to clear chips, so I got to come back out to 0 on my straight in. Got to clear some chips. I got to be very careful because there's very little clearance here. Okay, so first I'm going to do a sanity check. I'm going to make sure when I engage the half nut, which I can engage at any position, that it truly comes out. So it is coming out. I did not reverse the motion of the sled. You have a forward and reverse. If you're doing left-handed threads, you'd put it in reverse. I left it in forward, so I'm running the lathe in reverse, just like you were cutting a thread, like a metric thread on this lathe, and you've got to come out. You can't disengage the half nut, so you pull out, put the lathe in reverse, and come back out. That's essentially what I'm doing, except that we're going to cut. So I'm going to put this at 0, and we're going to go in to my Y0, and I think we can take a fairly aggressive cut. I'm going to do 20 thousandths for my first pass. Gauge the half nut, cut the thread, disengage the half nut, come back out to 0 so I don't clip off the tops of these threads. Take my Z-axis, or this direction, I guess you can't see it, that direction, towards the chuck. Come back to my 0 point. Clear some chips out of the way. Come back out to 0 on my X-axis. So when I talk about coming back to 0, I'm coming back out this direction towards these leaves so that I don't run into the threads I've already cut. Then we're going to go in. Oh, by the way, it's actually double 43 thousandths now that I just realized. Why? Because that was radial distance, and we need diametral distance, which is what my DRO is set to. I always forget that, shame on me. Which means, again, I need to go in further here. So I need to go in at least 100 thousandths on my relief cut, otherwise it won't be a relief cut. Take another cut. I'm paying very close attention between cuts to clear chips because it could be catastrophic if I don't. This being plastic, there might be a bit of deflection. Oh look, pulled the crap out all by itself. So we're going to do a spring pass. With metal, you definitely do spring passes because there's a lot of forces involved. I don't think it'll be as much with plastic. It may have been but the plastic itself might have actually compressed. So we're going to do one more at 86 thousandths, just to be sure. So there is a bit of compression on the plastic. Let me clear this out because the spring pass did remove some material. Now this is creating sharp threads, and I don't want so normally with threads you remove the top eighth. In a profile like this, you remove the top eighth of the thread, and then you wouldn't go down to the bottom. You'd lose the bottom quarter, eighth and quarter being of the total height of the thread, vertical height like this, towards the center. So, all right, so what I'm looking at here with the thread, these are 50 thousandths wide because it's 20 threads per inch, which makes this part 0.025. This part of the triangle is square root of 3 times 0.025, which is 0.043. That's the radial distance I need to go in, or double that, 86 thousandths, for the total depth of the thread. Now the top eighth of the thread, you're not supposed to have sharp points on your thread. You lose the bottom quarter of the total height, which is 43 thousandths, and the top eighth. So I need to figure out what an eighth of 43 thousandths is and go in twice that and just clip off the tops of all those threads so that I have a unified thread, standard compliant thread, I guess, if it makes sense. All right, so now without changing anything, I'm leaving the threading cutting there because what I'm going to do is I'm just going to clip off the top of all these threads, and the threading tool should be able to handle that. We're just going to remove 11 thousandths worth of material, so all my zeros and everything are set correctly, and I'm just going to come across, and I'm just going to go in very slowly. Okay, that's it. By the way, when you're done doing a thread on the outside and you file it, that's really what you're doing, is you're just removing that extra material on the top eighth. So you see I clipped the top of all these threads here. I'm just going to take some sanding paper in there and clean this out and make sure that my threads are nice and clean, and we can go on and make the next part. By the way, I'm holding this boring bar in an insert holder I made a long time ago for my radius cutters. This is just the handiest thing I have made in a long time. I use this every time I use one of these smaller tools so that you can actually get your tool post to set the right height, because otherwise you wouldn't be able to get there from here. And I've even got these little spacer pieces in here. It just all works out really great. Just small little set screws holding on the part. That's why I've got so many of them, just to spread the force out. Just works great.